Hi, my name is Mohamad Yaser Jaradeh, and I will be presenting here the ICWE full paper titled Better Call the Plumber, Orchestrating Dynamic Information Extraction Pipelines. This work is done by myself, Kuldeep Singh, Markus, Andreas both, and Sören Auer. This presentation is structured as follows. We will begin by going through a bit of introduction on the topic, then we will motivate the problem with a real-life example. Afterward, we will describe the approach in details. Moreover, we will go through the evaluation and what experiments we have done. Then finally, the future outlook and the conclusions of the current work are presented and discussed. Okay, so let's dive into it. As you may well know, knowledge graphs are becoming more and more used. They find their way into real-life applications and systems. A knowledge graph is a set of nodes, as you see here, also known as entities, and a bunch of relations in between those nodes. These are the relations also known as predicates. These knowledge graphs are usually not comprehensive. They lack data and they always need to be updated. In the example here, a toy knowledge graph is shown where Paris, the city, is described. We see some places located in the city like the Eiffel Tower or the Louvre. Of course, many other relations and entities can still be mentioned here. Mona Lisa, for example, with a relation to the museum, or Bill and Alice, where they visited the Eiffel Tower, and so on. Let's discuss a bit about these knowledge graphs. Many examples in real life actually exist. Freebase is maybe one of the most common knowledge graphs, or knowledge bases if you will. Wikipedia is one of the earliest knowledge graphs that also drove the research into the field. Wikidata, the Open Research Knowledge Graph, and Yago are but a few examples of open and domain-specific graphs that try to represent information in a machine-accessible manner. Now that we laid the groundwork about the knowledge graphs, what they have and how they are formed, we need to look at the advantages and disadvantages of conducting this. As mentioned previously, knowledge graphs are rarely complete. Thus, we always need to keep them up to date. And whatever missing entities and relations and triples, we actually have to add it to them always. However, this is easier said than done. A common source to populate a knowledge graph is natural language text. Natural language text itself is not a piece of cake. Human written text is usually ambiguous. It is unstructured and not easy to be processed by machines. The only upside of having natural language text is that we have a plethora of text online and in books that are just waiting for us to convert them into machine actionable knowledge and put them into graphs. For instance, here we have Harry Potter as a node, as well as Hermione Granger and Draco Malfoy. The idea of the knowledge graph completion here is to complete the gaps in the graph, which in this case is to add the friend relation. So we can add the friend relation between Harry and Hermione or Harry and Draco. But the thing is, depending on the context, most likely the text, you can find out that this is from between Harry and Hermione. That's the correct relation to add and not between Harry and Draco. We have seen a couple of toy examples so far, but let's look at a real-life piece of text that we will have as a running example, where we need to structure this piece of text and add it to the knowledge graph at the end. We have this text which says, Rembrandt painted the storm on the Sea of Galilee. It was painted in 1633. In order to make this small sentence machine actionable, we need to go through a series of steps to understand its components, and then we can transform it. First of all, we start locating the entities in the text. or named entities, if you will. Here, Rembrandt refers to the Dutch artist Rembrandt for rain. Another entity here in the text is Rembrandt's painting, The Storm on the Sea of Galilee. This is yet another entity that we need to keep an eye on when transforming the text to a knowledge graph triple. The next step is to find the relation between those entities. For instance, here painted links the artist and its work of art together. Relations are usually harder to spot than entities due to the complexities of natural language text. They can be implicit or explicit as well as expressed in different ways. Case in point, with the other relation painted in, it has a surface form, or the text of it, that is similar, if not exact, to the other relation. And yet, it has a totally different meaning than the first one. Furthermore, upon looking at the text, we notice that the literal, also known as a ground value, 1633, has a relation or is correlated to the relation painted in. And the final piece of the puzzle is the pronoun it. This pronoun here shows one of the ambiguities of natural language text. The it here refers to the entity, the storm on the Sea of Galilee, and should be replaced by it at every step of processing of the text for the text to make sense or to have a full meaning. Okay, now that we looked at the components per sentence, let's see if we can get the meaning or the semantics, if you will, out of it. As we mentioned already, Rembrandt relates to the Dutch artist here. The first relation, painted, points to the action of the artist painting a work of art. The second entity, the storm on the Sea of Galilee, links to Rembrandt's painting. Painted in, the other relation refers to the time or the date when this was done. The pronoun it is something we already know, that it refers to the storm on the Sea of Galilee. And finally, the value 1633 is the date or the year when the painting was made. So, now that we know the working pieces of the text, assuming that we want to link this text to DBpedia knowledge graph, we get two aligned triples out of it. One that explains the relation between the artist and the painting, this first triple here, and the second triple describes what year the painting was made in. You can see, for instance, that the relation painted, the first one, is mapped to DPO or DBpedia ontology artist, while the second one painted is mapped to DPP, DBpedia property year, which refers to the year property of things. Okay, so we described the problem. We will now take a look at our approach of addressing said problem. We noticed that the research community is always coming up with new tools and techniques to manage minor issues of small tasks in the information extraction world. These small tasks that we care about in this articles are the following: the entity extractors and linkers, these tools that find named entities and map them to corresponding knowledge graphs. Another type of task is the relation extraction and linking, which also detects dimensions and of relations and maps them to a knowledge graph. Third one is triple extractors, which is another set of tools that we can make use of in our work here, where triplets of the form subject, predicate, and object are extracted from natural language text. And finally, coreference resolution tools are essential to disambiguate pronouns or acronyms to their original mention. However, all these efforts are separate, and we would like to put them under one umbrella with our work here, Plumber. Going back to our running example, we need a pipeline of the previously mentioned small tasks, or information subtasks, if you will, information extraction subtasks. As you see, each task extract and process one piece of the puzzle, and we need all of them to find out the correct answer or the complete answer. However, these tasks should be in the correct order. Due to the fact that these are components in a pipeline, these needs to be in the correct order because one element feeds its output to another as an input. And as such, this is how our pipeline looks like at the end. Starting with the raw natural language text, the first step is resolving any ambiguity from pronouns or acronyms. Then, triple extraction operates on the unambiguous text. Afterwards, entities are linked, and finally, relations are extracted and mapped. And the result of such pipeline is a set of aligned triples that can complete a particular knowledge graph. So, why Plumber? As mentioned, we have a set of tasks that are being developed in the community to perform different IE subtasks, and we can put them together to perform knowledge graph completion or information extraction. Plumber also highlights the difference between static pipelines and dynamic ones, and how choosing a suitable pipeline based on the input can affect the overall performance of the approach. Now that we introduced Plumber, let's discuss its architecture. Plumber is modular. It has a pool of components that perform the different IE subtasks. A pipeline generator module that creates all possible pipelines and sets them up in the pipeline pool for use later on. A composed pipeline doesn't have to contain only one component per task. Rather, any combination of components can be used. Case in point, pipeline A, pipeline 1. On top of all of that, a selector module that employs a Roberta transformer model that chooses a suitable text depending on the input text, or chooses a suitable pipeline depending on the input text, and a set of requirements such as the knowledge graph it needs to map to. Lastly, a pipeline runner module that takes the input text and the suitable pipeline that was generated via the pipeline selector. It runs the pipeline and retrieves the set of results. One might ask or wonder, why dynamic pipelines? Wouldn't one great pipeline resolve all our issues? Unfortunately, that's not the case. As you see in this example here, in order to extract the two triples encoded in our running example about Rembrandt and his painting, we illustrate three possible pipelines and how each one of them has different result at each step. Pipeline 3 here has the best result, or the correct one. The coreference resolution tool here, Neural Coref, is able to correctly resolve that it belongs to the painting, unlike the resolver in the first pipeline. The combination of the two triple extractors is needed to get the correct triples. And finally, the joint entity and relation linking tool, Falcon, was able to map all the parts of the triples correctly to a knowledge graph. And of course, you can find a case where this pipeline doesn't work on a text, thus highlighting the need for a dynamic aspect in the workflow. We jumped a bit over the module or the model that we selected in the architecture because we will be discussing it here. We make use of a transformer model. We choose this kind of model because of its ability to generate rich semantic representations and contextual embeddings of text. A transformer model is pre-trained on massive amount of text, and we just need to fine-tune it on our specific task, which in this case, it is classification. Our model of choice was Roberta. How we did this, we trained Roberta to perform sentence classification. We processed each natural language text sentence in the dataset as input, and the output was a suitable pipeline for mentioned sentence. In order to obtain these, we had to run all possible pipelines on all possible inputs and choose the best performing pipeline per input as the truth value for its classification output. As an example, here the input will be our running example, and the output would be the class of this pipeline, which is the combination of these 4 components together. And this would be done for all sentences or all text snippets in the input dataset. For the implementation details, we have created Plumber in Python. It is open source and is available online under this GitHub repository. While designing Plumber, we had 3 principles in mind. The isolation principle, to allow components to run separately in different environments without affecting each other. The reusability, where all components can be reused via their code or APIs. And finally, extensibility, where all main components of Plumber have interfaces that can be easily extended for future components or specific cases. More into the evaluation, we evaluated our framework on 2 knowledge graphs, DBpedia and the ORKG. DBpedia is an open domain knowledge graph. It has been in the community for a while now. It is generated from Wikipedia info boxes. And overall, all available languages, it has a stunning 11.5 billion triples. On the other hand, the Open Research Knowledge Graph, or the ORKG, is a domain-specific knowledge graph. It is oriented only for scholarly knowledge. It is much more recent than DBpedia, and it relies on publications and scholarly articles as data sources. It has a modest 1.5 million triples. Next are the datasets used for the evaluation. We used 2 datasets, the WebNLG and COF triples. The Web Natural Language Generation dataset is part of the WebNLG challenge to convert text to DBpedia triples and vice versa. It has around 46,000 triples. The other dataset we use is related to COVID-19 knowledge. It is aligned to the ORKG. It has been manually annotated from the abstracts of 21 publications about COVID and has 75 triples. Finally, the baselines before we go into the individual experiments. We ran our experiments against 2 baselines. T2KG, which is an end-to-end triple alignment system, and it works on DBpedia. The other baseline is Frankenstein, which is a framework to compose dynamic question answering pipelines. It uses logistic regression to greedily find a so-called best pipeline. We adapt its pipeline selection approach as one of our baselines. For experiments, we first benchmarked the static pipelining. A static pipeline is the best performing pipeline overall. It will be used for all the input text. As we see in this table, though Plumber outperforms the other baseline, still the overall scores are not high enough. On DBpedia, the best F1 score is 21%, and on the ORKG, it is 41%. So we train our model to dynamically select a suitable pipeline. Here you can see the precision, recall, and F-score of the classification. Using Roberta showed a much better performance than just using plain logistic regression as in Frankenstein. With that in mind, after training, the dynamic pipelining is evaluated. Dynamic pipelining means here that every input could have a different pipeline to run on. The table shows that dynamic aspect improve both Frankenstein and Plumber. Plumber is still the overall winner, however, the results are not that satisfying. So, we would like to investigate what is the cause of this low accuracy overall. So we performed a comprehensive ablation study for each of the tasks we mentioned earlier. We study the effects of several cases and variations of the input on how different components perform depending on that. Here we start with the coreference resolution tool. We focus on the length of the coreference chain, which means the number of aliases for a single mention. Additionally, the number of clusters is another criterion in the analysis. A cluster refers to the group of mentions that require disambiguation. The presence of a proper noun in the sentence is studied as well, with acronyms. Furthermore, the demonstrative nature of the sentence is also observed as a factor. Demonstrative sentences are the ones that contain demonstrative pronouns, such as this and that. From this heat map, we can see that neural coref and HMTL are the overall winners, but the values differ based on which criterion is in the text. Next up is the triple extractor. Here we focus more on the number of words, or WC. In the input sentence, the sentences with a higher number of words than 7 are considered complex sentences, at least depending on the data set we have. Furthermore, having a comma on a sentence, or a subclause if you will, to separate clauses is another factor to study. Atomic sentences such as cats have tails are a type of sentences that also affects the triple extractor's behavior. Moreover, nominal relations as in Durin, son of Sören, is another impacting factor on the performance. Uppercase and lowercase mentions of the word, which means the correct capitalization of the first character, not really the entire word, is also a standard error source for entity linkers as well as other components in the pipeline. We can see from the heat map that no component excels in all the cases, but overall a couple of components such as OpenIE and Graphene show the best prospects. The same is true for entity linkers. Instead, we focus our criteria on the entities themselves, like the casing of the entities and the number of words in the entity surface form. The nature of the entity plays a role here, as well as if the entity is explicitly mentioned in the text or implicit. By implicit, we mean parts of it is mentioned or a synonym is mentioned, rather. Same observation go that no component is the overall winner, but for instance, Falcon here has an overall average score of maybe 50 to 60, 55 to 60%, and that's maybe one of the best performing. Finally, relation linkers are studied similarly to the entities, where we focus on the surface form of the relation and the nature of the relation, whether if it's explicitly mentioned or hidden. We also noticed that relation linkers seems to be a bottleneck of performance, because the best performing component has an average score of around 35% total. Last but not least, what we gather from our research is that Plumber, with only 33 IE components, was able to generate 264 pipelines. We conclude that using contextualized embeddings, it is much better for finding suitable pipelines than other methods. We also note that we found that pipeline-based or component-based pipelines are better performing than regular end-to-end pipelines for different input text. For future work, we would like to extend Plumber to other knowledge graphs such as Wikidata or UMLS, Currently, Plumber only supports English, and we would like to address the multilinguality of things. As well as we want to create some high-performing component, especially relation linkers, and see how do they impact the overall performance of the system. That was it for this presentation. There's a demo of a UI integration for Plumber available online on YouTube. You can see it, and an interactive demo will be available soon for everyone to try it out. Yeah, thanks for listening and thanks for the attention. Questions?